Welcome to topic 9 of CP0. So this is the second to last topic in this course. In this topic, we want to talk about two things. First, we want to cover two efficient sorting algorithms, quicksort and merge sort. And then we want to talk about how to do simulation problem, which often involve sorting events. So in previous topic, I believe topic 5, we studied the three sorting algorithms: bubble sort, selection sort, and insertion sort. They all have a worst case complexity of big O n square, so they're all quadratic. When the data to be sorted is there are a lot of them, when it's large, then this is not efficient enough. And when sorting it's done using comparison, so that is we compare two elements and then decide which one should go before the other. This has a lower bound of a big O n log n. So by lower bound we mean that it is not possible to have an algorithm that has a lower complexity and that can work for all cases. So it may be the case that the algorithm will take a shorter time when given some input. So for example, even using bubble sort, if the array is already sorted, then it only takes linear time. But there will be input where bubble sort takes a lot of time. So when we talk about the worst case complexity, then using comparison, it's not possible to do it with lower than n log n. And here is a short proof. So given n numbers, let's assume the case that they're all different. So then there are n factorial different permutations in them. Now suppose the sorting algorithm uses m comparisons. So each comparison can only have two outcomes. So it's depending on whether you're less than or less than equal, but this comparison can only have two outcomes. So therefore, if we use m comparisons, there are 2 to the m possible outcomes. So in order to sort this correctly, each of these n factorial permutations must belong to one of the 2 to the m possible outcomes. So it is not possible to have two different permutations that fall into the same outcome and then still sort them correctly, because we wouldn't know. So suppose we have two permutations and the only thing they differ is the position of two elements a and b. One of them has a before b, the other has b before a. Now if they are these two permutations have exactly the same outcome for all the m comparisons, then you don't know which one is correct. You don't know whether A should go before B or B should go before A. There's no way to sort it correctly. So therefore, in order to sort all the different n factorial possible input, we need to make sure that the possible outcome has to be at least as large as the possible input. So in other words, 2 to the m has to be greater than or equal to n factorial. Now if we take a log, base 2 log at both sides, then we will have m has to be greater than or equal to log of n factorial. And this turns out to be big O n log n. So if you know the Stirling's formula, you know that log n factorial can be approximated by n log n, or in the exponential form is n factorial is can be approximated by n to the power of n divided by e to the power of n. But we can also prove this without using that. So for example, log n factorial is essentially the sum of n terms, log n plus log n minus 1 plus log n minus 2 and so on. Now if we just look at the first n over 2 terms, then each of them is at least as big as log n over 2, which is log n minus log 2, which is 1. So log n minus 1. So then we have at least n over 2 of them. So that means we have at least n over 2 times log n minus n over 2. So that's asymptotically, if we ignore the smaller term and ignore the constant, that's n log n. So yeah, so this is the lower bound. In general, for sorting, our goal is to do n log n because it's not possible to do lower. To have an algorithm that takes shorter time. And this is generally something that will be covered in algorithm course, but the basic idea is actually fair. I think it's fairly simple for those who have the mathematical knowledge. So this lower bound doesn't hold when we do counting sort. Because counting sort can be done in linear time. In counting sort, what we are doing is we essentially scan through all the items and then count how many of each item occurs, and then we simply output the items and duplicate them accordingly. Counting sort works when the range of the item is small. So if we only have up to, say, 10 to the 6 possible items, then we can sort arbitrarily big array in linear time because we just need to scan through them and counting at the same time, and then printing out the result. But that's only works when the domain is small, so we can use counting sort. More generally, they cannot. they are not always applicable. Okay, so in this topic, we're going to introduce two sorting algorithms that have average case complexity bigger than log n. So these are the algorithms that are actually used a lot in libraries for sorting. So we're going to take a look at them.